something impossible just happened in deep space. We received a chemical fingerprint that shouldn't exist, and it's rewriting everything we thought we knew about visitors from beyond our solar system. The data streaming in from NASA's SPHERICS mission has revealed that the object we're tracking, known as 3I Atlas, is behaving in ways that defy our models of how these cosmic travelers should act. Right now, somewhere between the orbits of Mars and Jupiter, an ancient world is tearing itself apart, and the secrets spilling out are forcing us to question the very nature of planetary formation across the galaxy. The object is currently positioned between 3.8 and 4.0 astronomical units from the Sun, receding from us at roughly 40 kilometers per second as it glides through the constellation Gemini. Its apparent brightness has dimmed to a magnitude between 13.5 and 14.2, placing it beyond the reach of amateur telescopes. But what professional instruments are capturing tells a story of unprecedented violence and activity. This isn't a dead rock coasting through the void. This is a geologically active body that is convulsing in response to its recent encounter with our sun's warmth, and the chemical composition of what it's releasing is nothing short of extraordinary. The infrared emissions we're detecting reveal a potent cocktail of water vapor, carbon dioxide, methane, methanol, and cyanide pouring out of this object in massive quantities. But here's what makes this truly bizarre. We typically expect cometary activity to peak when an object is closest to the Sun, reacting to maximum solar heating. Yet this major release of volatiles is happening as 3I Atlas is moving away, receding deeper into the cold outer solar system. This suggests that the heat from its closest approach took time to penetrate the surface layers, finally reaching a reservoir of frozen gases trapped beneath a protective crust. What we're witnessing is the delayed response of an interior that has been locked in stasis for billions of years, now suddenly exposed to warmth for the first time since this object formed in the darkness around a distant star. The presence of water vapor is expected in any comet, but the simultaneous and significant detection of carbon dioxide, methanol, and cyanide in these quantities points to something far more primitive and chemically diverse than the comets native to our solar system. This is pristine material that has been shielded from cosmic radiation and heat, locked away in a frozen time capsule until this very moment. The intensity of these emissions indicates we're witnessing the shedding of the object's outer skin, or perhaps the catastrophic fracturing of a weathered crust that is now exposing fresh, volatile-rich ice directly to the vacuum of space. The detection of cyanide is particularly revealing. In solar system comets, cyanide typically appears as only a trace component, a minor player in the chemical symphony. But here it manifests as part of a robust, distinct outflow, suggesting chemical abundances that simply don't match what we see in our local neighborhood. This chemical diversity implies that 3I Atlas did not form in a warm, processed environment close to a parent star. Instead, it likely coalesced in the cold, dark outer reaches of a distant stellar system, far from its sun's radiation, allowing these volatile compounds to freeze into the very architecture of the nucleus without ever being altered by heat or pressure. What makes the SPHERICS data so powerful is its 102 wavelength infrared capability. This technology doesn't just detect these gases, it maps their relative abundances with unprecedented precision. We're seeing spectral lines that are directly linked to the sublimation temperatures of specific ices, and the fact that they're all releasing simultaneously at a distance of nearly 4 astronomical units reveals something critical about the thermal properties of this object. It holds on to heat, it takes a long time to warm up, and consequently takes a long time to cool down. We're seeing thermal lag in action, where the peak temperature of the subsurface creates peak activity long after the perihelion point has passed. This chemical fingerprint also reveals the physical nature of the material being ejected. We're not just seeing gas escaping into space, we're seeing the ejection of large grains and solid chunks, some the size of BB pellets. This is a crucial distinction. A typical fluffy cometary snowball would disintegrate into fine dust under thermal stress. The presence of these larger, substantial grains suggests that the nucleus of 3I Atlas is compact and resilient. It has structural integrity that is holding it together despite the violent outgassing tearing at its surface. This resilience stands in stark contrast to the fragile nature of many comets native to our system, which often crumble under far less thermal stress. But within this broad chemical surge lies a specific anomaly that demands deeper examination. While water vapor and carbon dioxide began venting earlier in the object's journey, the appearance of methane has been significantly delayed, showing up only after the object had already passed its closest approach to the Sun. This timing is extraordinary because methane is extremely volatile. It should have sublimated and escaped long before water ice did. The fact that it waited until now to emerge tells us something fundamental about the internal architecture of 3I Atlas. Methane now comprises between 14 and 27% of the total water production, making it a dominant component of the current outgassing. Even more remarkably, the data shows that the relative abundance of methane is actually increasing as the object departs the solar system. This behavior points directly to a layered nucleus model. It implies that methane was not present on the surface when the object entered our system. Instead, it was buried deep beneath an outer layer of other materials. Only after those outer layers sublimated away, stripped by the heat of perihelion, was the inner methane-rich core finally exposed to space. This delayed release suggests that the interior of 3I Atlas has been pristinely preserved despite traveling through interstellar space for potentially billions of years, bombarded by cosmic rays and exposed to the harsh environment between stars. The core remained shielded. The outer layers acted as a sacrificial crust, a radiation-hardened shell that protected the delicate volatiles inside. When that shell was finally breached by solar heating, the methane trapped inside was released in a delayed, explosive event. This confirms we're looking at a differentiated body, one that was built up in layers over eons, rather than a homogeneous lump of ice and rock. The chemical strangeness extends beyond just the timing of methane. The observations indicate that the ratio of carbon dioxide to water is unusually high, sitting between 8 and 10. This is one of the highest values ever recorded for any comet, whether from our solar system or beyond. Most comets in our system have a much lower proportion of carbon dioxide relative to water. This extreme ratio is a smoking gun for the object's formation history. It suggests that 3I Atlas formed in a carbon-rich environment, likely in the outer disk of a distant star, where carbon monoxide and carbon dioxide were far more abundant than water ice. This high carbon content separates it from the family of objects we're familiar with and hints at a birthplace that was chemically distinct from the nebula that spawned our sun and planets. Understanding why the most volatile gas waited the longest to appear requires us to rethink standard models of cometary evolution. In a typical model, volatiles release in order of their sublimation points: nitrogen and carbon monoxide first, then methane, then carbon dioxide, and finally water. Here the sequence is scrambled because physical layering is overriding chemistry. The methane couldn't escape because it was physically trapped beneath other materials. This implies a complex formation process where the object gathered different materials at different stages of its growth, perhaps migrating through different regions of its home protoplanetary disk. The delay also helps explain the continued activity we're seeing at nearly 4 astronomical units from the Sun. Methane turns to gas at extremely low temperatures. Now that the methane reservoir is exposed, it can continue to drive activity even as the Sun's heat fades. The water ice activity will shut down first as the object cools, but methane and carbon dioxide can keep the vents open, powering jets and expelling dust far longer than a water-dominated comet could sustain. This differential shutdown will likely cause the coma's composition to change drastically in the coming weeks. The sheer quantity of methane, up to 27% of the water production, is staggering. It implies that this inner layer isn't just a small pocket, but might represent a significant portion of the total mass of the object. We might be dealing with a body that is fundamentally a methane world, disguised for most of its journey by a water ice shell. This inversion of expectations is precisely why interstellar objects are so valuable. They challenge our assumptions about how planetary systems are built. The release of methane is energetic and expands rapidly. This intense, delayed outgassing provides the thrust necessary to eject the large grains we detected in the infrared spectrum. It's the engine behind the post-perihelion brightening we're witnessing. The pressure from sublimating methane is likely fracturing the remaining crust, creating the vents and jets that define the object's current appearance. But this gas isn't seeping out uniformly. It's bursting out in specific directions, shaped by the geography of the nucleus and the physics of the ejection. We were incredibly fortunate to catch 3I Atlas during a rare, near-perfect alignment between the Sun and Earth. The viewing angle was just 0.69 degrees off-axis. In astronomical terms, this is effectively looking straight down the barrel of the gun. This specific geometry allowed us to see structures that would have been invisible from any other vantage point. The Hubble Space Telescope data reveals unprecedented jet structures emerging from the nucleus. We're seeing 3 distinct mini-jets spaced at regular 120-degree intervals. This symmetry is striking and highly unusual. Typical cometary jets are often chaotic or clumped together on the sunward side. To see 3 evenly spaced vents implies a high degree of order in the underlying structure, or perhaps rotational stability that organizes the outflow into this trifold pattern. This alignment also revealed an extended anti-tail, a sunward-pointing spike of dust that appears to defy the solar wind. However, this is an optical illusion caused by our viewing geometry. The anti-tail consists of larger, heavier particles, likely the BB-sized chunks we detected, that have been left behind in the object's orbital plane. Because they're heavy, they lag behind the nucleus, and when we view the orbital plane edge-on, these trailing particles appear to project forward toward the sun. The alignment also explains a sudden 20% surge in brightness that was recorded. This wasn't necessarily an increase in material coming off the object, but rather an effect of dust scattering light directly back at us. This is known as the opposition surge. The dust particles, particularly those large grains driven by methane release, hide their own shadows when illuminated directly from behind the observer, resulting in a spike in apparent luminosity. By analyzing this surge, we can deduce that these particles are not smooth spheres, but rough, porous aggregates that scatter light efficiently in the backscatter direction. The presence of 3 mini-jets at such precise intervals highlights the asymmetric nature of the coma. The gas and dust are not forming a perfect sphere around the nucleus. Instead, we see a lopsided cloud with outgassing patterns, distinct from typical solar system comets. This asymmetry is likely driven by non-uniform mass loss. If the methane outburst is localized to specific fractures or regions where the crust has failed, it creates concentrated beams of material rather than a global fog. The jets are not just surface features, they extend far out into the coma, shaping the overall environment. The fact that we can distinguish individual jets at this distance speaks to their intensity and collimation. While Hubble gave us a snapshot of this structure, NASA's TESS mission provided the movie. In a dedicated campaign, TESS compiled a 28-hour continuous video sequence constructed from 36 individual frames. This high-cadence monitoring revealed that 3I Atlas is not rotating smoothly. It exhibits unstable rotation with varying periods, a state often called tumbling or non-principal axis rotation. The light curve shows periodic fluctuations that don't repeat perfectly. A simple spinning top would give us a clean, predictable sine wave of brightness. This object gives us a messy, complex signal, indicating the nucleus is tumbling end over end, likely spinning on multiple axes simultaneously. This chaotic motion is a direct result of the outgassing we've been analyzing. The jets of methane and water are acting like thrusters, but because they're distributed asymmetrically, they're applying torque in varying directions, constantly destabilizing the spin. Along with this tumbling motion, TESS observed an overall fading in activity during the observation window. The peaks in brightness were getting lower and the troughs deeper. This fading is a signature of the object moving away from the sun and activity beginning to wind down, but it also hints at the exhaustion of specific active vents. As a pocket of volatile ice depletes, the jet shuts off, the torque changes, and the spin evolves. Ground-based observations from major telescopes like Gemini North, Subaru, the VLT, and Keck have corroborated this picture of instability. They depict an increasingly asymmetric coma dominated by dust. The main tail, usually the most prominent feature of a comet, has nearly vanished in recent images. What remains is the weak anti-tail and a diffuse, lopsided cloud of dust surrounding the central point. This lack of a strong main tail confirms that fine dust has either been blown away or production has ceased, leaving only larger, heavier grains that linger near the nucleus. The link between the coma's shape and the nucleus's spin is crucial. As the object tumbles, different faces are exposed to the sun. If one side has a large, active region and the other doesn't, the amount of material released changes drastically as that face rotates into and out of sunlight. This chaotic spin also complicates attempts to measure the precise size of the nucleus. However, the fluctuations give us constraints. The fact that spin is changing implies the mass is low enough to be pushed around by gas pressure. A massive planet wouldn't notice a geyser on its surface, but for a small cometary body, a strong jet is a significant mechanical force. The video data essentially shows a body physically convulsing as it recedes into darkness. Interestingly, the periodic brightness fluctuations aren't random noise. There's a pattern within the chaos that allows astronomers to tease out spin rates. While the period varies, it generally falls within a range, suggesting relatively fast rotation, which helps explain the centrifugal force needed to eject larger particles. If it were spinning too slowly, heavy dust might simply fall back onto the surface. The spin helps fling it into the coma. Given what we now understand about the forces pushing this object around, we can finally refine our estimates of its physical properties. The latest analysis has pinned down the nucleus diameter to 2.6 kilometers, plus or minus half a kilometer. This assumes a surface reflectivity of roughly 4 to 6%. As dark as fresh asphalt, this size is significant. It makes 3I Atlas the largest and most massive interstellar object we have ever observed. The mass estimate is equally impressive, coming in at 5 to 7 times 10 to the power of 12 kilograms. To put that in perspective, this object is over 40 times heavier than Borisov, the only other confirmed interstellar comet we've studied in detail. This substantial mass helps explain why the nucleus has remained resilient despite violent outbursts and the mechanical stress of chaotic tumbling. A smaller body might have fragmented under the pressure of methane release or centrifugal forces of its spin. But 3I Atlas has the self-gravity to hold itself together. Polarimetry data from Gemini and VLT telescopes adds another dimension to our understanding. The observations reveal a deep negative polarization branch of minus 2.7% at a phase angle of around 7 degrees, with an inversion point at roughly 17 degrees. This measures how dust grains scatter polarized light, and these specific numbers indicate unique dust properties. We're likely looking at large, fluffy aggregates or unusual mineralogy not common in solar system bodies, reinforcing the idea that the materials building this comet compacted in a completely different stellar environment. The European Space Agency's JUICE mission has confirmed ultraviolet signatures and the presence of dual tails. The plasma particle data collected by JUICE adds to the picture of a body interacting with the solar wind, creating a complex bow shock as it travels. These findings position 3I Atlas as the most active interstellar visitor yet. It's not just the biggest, it's the most dynamic. The exotic chemistry, the stratified structure implied by methane delay, the symmetric jets, and the sheer durability all paint a picture of an object that challenges standard models. Anomalies like early activation at 3.5 astronomical units, minimal non-gravitational acceleration despite the jets, and the distinct lack of a main tail in later stages suggest we may need to revise theories of how interstellar objects evolve. This is not a standard comet. It's a durable, layered, carbon-rich traveler that has survived a journey of light years. As it approaches Jupiter, passing at a distance of 0.36 astronomical units, the gravitational influence of the gas giant will be the final chapter in its solar system adventure. However, by that point, activity is expected to fully subside. The methane will deplete, the crust will refreeze, and the object will go dormant once again. This brief, violent visit has given us a glimpse into the chemistry of another star system. It has shown us that the galaxy is populated by bodies that are both familiar and deeply alien. We've learned that delayed methane release can preserve ancient ices, that tumbling rotation is a natural consequence of stratified outgassing, and that interstellar objects can be massive, resilient survivors. The story of 3I Atlas is far from over. As it fades into the dark, it leaves us with more questions than answers, which is exactly how science advances. We'll be studying this data for decades. Only by analyzing these fleeting visitors can we hope to understand the universe beyond our own sun.